step, you can send this machine to a very simple digitally controlled machine that is, in this case, it's a 5-axis router, could also be a 3-axis router with this principle that translates this digital information that, as you have seen, is generated on a very, very low resolution screen with a very simple application, so not targeted at professionals, but as laymen's, then is transferred to this maybe 20 numbers that are parameters, and then gets translated back through this very simple machine into wood, walnut wood, and creates this very beautiful, very elegant, very expensive and precious piece of furniture that is at the same time sort of elegant and strange. So questioning the notion of design to a certain extent, because a table is not meant to have holes in it. Or let's say if you do holes in a table, then you need a special reason. So and then the whole questioning about who is the author, is the designer of the application, so of the algorithm, the author. What is the role of this? What we back at this time called the co-author, that is the person that gets the application and manipulates this or plays this game, and then at certain points decides to start this process. So of course it's not that simple, because in between you have also to make a payment that back at this time was not that simple as clicking on or answering yes. And this was about a lot of money. You can imagine such a table from the material, the process, and so on. But basically, this decision of saying, okay, I like this, and I wanted this produced, materialized, and then sent to my home was the whole challenge behind this project. It was not a commercial project, of course. It was more about observing what would happen in a real setting, because we sold about 10 tables, and to find out what this change would mean. So being able first to produce data, to get aware that we produce data, everything we manipulate on our devices, we produce data, and that this data can be translated back into the material world. What you see on this slide is just a collection of unbuilt tables with different dimensions, different colors, different topographies, shapes of this underside of the table, that at a certain point, if the table gets lower than 30 centimeters, flips on the other side, so it becomes the upper surface. And what is interesting here, behind each one of those designs, you have an author, so somebody that spent time thinking of what he or she liked or didn't like, and so on, and then at the end got insecure or just didn't have the money, so didn't complete this process. But if you look at the array of those things, you will not concentrate on the fact this one is nice and this one is ugly, this is functional, this is not. What the image says is that at the end of the day, they are all very similar. And what is the conclusion we took of this experiment? There are many things. I mean, it's an ironic approach to design and so on. But the most important conclusion for us as architect of this project has been that we should not fear letting the form out of our control. Form somehow for architects, but the designers is the holy graal. It's where the professionality and their competence comes to and if you delegate this to somebody else, but if you design very carefully the rules of the game, then this is the message of the project, then you're still very much under control, just on a higher level. So you're not designing or defining the details of it, but the bigger picture. And this is a thing that throughout our work, that is a lot about parameterization, about deciding what should be defined by whom at which stage of the design, and how things are then transferred into reality. So when do they get freezed is very important. The second project that I would like to show, or to explain this approach to parameterization we have in our office, is a single family house that is newer than the table. It's a small piece of architecture, of classic architecture. It's, as you've seen here, a small village in Switzerland, nearby a lake, a very protected area. This is the situation. And you see the house has sort of a special, strange shape for a plan. If I now explain you how this shape is motivated, and the shape is very easily explained by two intervention. One is keeping the view of the house on the right that belongs to the same client. So the client basically was building in its own garden, and this view is the view on the lake. Then you will understand that cutting this one edge has been very important, and this is a very normal operation we do while designing. We don't even think about what this means. And the second one, you see it here, is the access with the car to the house. So if you say you want the car on the back of the house, so not on your lake side, on your view side, then you have to make a second cut in order to be able to drive in. So these two very simple parameters that balance each other, because if you give a bit more side, then I have less space, and then I get a problem on the other side. What is a very conventional, let's say, design operation that we do every day without, as I said, being really conscious about this. This is just nothing else than a parametric operation that leads to this floor plan. Now, why am I showing this to you or saying this banal thing? It's because it's important to recognize that for this parametric operation, we don't need any computer, because we are able to cycle through this problem in our head, in our imagination, or just by sketching something quickly enough to find a reasonable solution in a reasonable amount of time, and to come up with this design that is one of many possible, but is one valid option. Now I show quickly how the house works, just to or give you orientation, but not talk about the architecture of the house. See, you have here a core housing the staircase and the kitchen and bathroom, very classic, and the open floor plan around it. The core goes up to the second story, and a cantilevering roof, concrete roof, is deposited on it. And here you see the facade. On the facade we have a window following the roof, 1.50 meters, all around the house. Now the problem was in this very protected area that this was just too much glass to get approved by the authorities. So the trick, we did this trick already once before, is to clad the whole house with wood, because wood is a material that is accepted, belongs to the environment, so slats, but to place them perpendicular to the facade in order to have this effect. So basically you close the whole thing, and when looking from a perspective, you don't see the glass anymore. It's only if you have this frontal view. Now, From far away, it looks like nothing would happen. If you go a bit closer on the image on the right, you see that, in fact, something happens on this structure. And what happens? This happens. You see, those slats are processed. So each one gets cut symmetrically on the front and then back side just by slimming out the section. It's the first operation, and then on the plan on the bottom of the image, you also see that these two cuts can be they are also always parallel, but they can be tilted. And what does this generate in the sequence? Nothing else that controlling your field of view, because if you have a series of slats, the depth of the slat define how wide your visual finally will be. And by controlling also this angle, you can influence if your field of view is more open on the light and or on the left. This again is a very, I would say, simple traditional approach to design, because what is all about is about controlling privacy, controlling energy, so where should the sun come in, controlling view, controlling the relationship between the inside and the outside, and this architectural device is nothing else than a device to control it. So one is the opening itself, that in this case is rather undifferentiated ribbon of glass following and the second one is this. Now, from this point of view, this operation is very comparable to the two cuts on the floor plan. Now, the difference here is that with this parametric operation, having 315 in this case different slats that have a different height and are cut at a different position, you run into a big problem, because the first question is, how do you design those slats? So if you want to model them all, it will take you a few days to go around the house, and then you have just done one iteration, and each one depends on its neighbor. So if you modify something on one slat, or a position of a window behind, or if you say, okay, I want it to the left and not to the right, then you have to remodel all 315 wood slats. Each one is not very complex, but because they depend on each other geometrically, this operation is very, very time consuming, and you would probably lose overview very quickly. So what is the result of this? That you will not do it just because you are not crazy, you don't have the time, you don't have the money to do it. Now, if you program this task, like we've seen in the table, because at the end it's a very simple geometric operation that is behind, then you can start to design the whole thing, So you have a reason, a really good reason here to deploy parametrics, to deploy programming, because otherwise you will not be able to do the design job. Now, the design job is only the first part of the problem here. The second problem is, admitted that you have these 315 geometries on your computer or drafted or wherever, and that they are all fine, who will produce this and how in reasonable budgets? Because the cutting the single slats will not be the big deal, but making sure that the geometry is transferred the right way from the computer to the physical slat, this is the dangerous or time-consuming thing. In this case, there is one machine that has been conceptualized in the design since the beginning that does this job, because it's nothing else than a mill that is passed along a slat and that is able to modulate, so to change its Z height, and at the same time also to tilt. It's a very simple machine. This machine is used every day to bring slats to the right height and to smoothen the surface. So what we do here is just intervene in a machine that exists that is used anyhow, that normally passes through without changing its depth position or tilt. And we do the same thing just by controlling the machine with the data that we automatically produced because we decided to program this 315 slats. So the logic of the house. What would give us as a free output the geometries of the slat. And in the end, you get this very simple result here that is a bit hard now to read in the images, but I think you can imagine it's a thing that while moving inside and outside the house changes your relationship to the outside or to the inside if you are outside. And the beauty of this intervention is that there is nothing additional. You know, the slats were needed for the building code. It's no decoration. The only thing that is introduced is a intervention, a parametric intervention with a architectural motivation behind that produces data that can be transferred to a machine that runs anyway. So it's cheaper than painting if you want, you know, to create a rather interesting effect. Now this all sounds very simple. It's not, because there are very many processes in between. So first you have to decide how you do it, then you have to spend a lot of time parameterizing this thing, and then it gets really hard when you have to find the contractor that is willing, you know, to have you basically controlling his machine. And all those things are not in place yet, you know, because they are used. The transfer of data happens on another level where people do know what they get. You know, if we send 315 files on a machine that we do not own, we could just destroy it, you know, because if this data is wrong and the contractor doesn't have really a tool to verify this. So what I'm talking about, these things are in their infancy, and probably in the next few years there will be need for the definition of new interfaces, but also of new legal interfaces between the producers of data and the owners of the tools, the machines that are able then to produce architecture. So we come now, after this introduction on the background of our work, to this question of the machine that for us came up now almost 10 years ago when we were appointed as assistant professor at this time at ETH in Switzerland in this domain, new domain of digital fabrication, where we collected some experience, but it was more sort of intellectual experience with those experiments, and being then asked to do research in a technical university confronted us with the question in the beginning, what machine would be good to do this? And the beginning of the century, the most spread machine in architectural investigation was, of course, the mill. Think of Greg Lynn, for example, that introduced it in academia, but also in his office. And we felt that the mill, for example, although it's a wonderful machine, we used it in many projects, the table and so on, but it would constrain the focus area of our research too much, because the mill is a specialized machine, like many others. It's a machine that has been designed with the clear focus on one single process. And this process of optimization has one advantage, that the mill is very fast and very precise and doing milling. And the disadvantage is that the mill tells you can mill. And to modify a mill and do something else, and there are schools that do this, it's very hard. And as a contrast to the mill or to specialized machine, we choose to buy an industrial robot, because an industrial robot has a series of advantage being the first one, the crucial one. The robot is a generic machine, a generic tool. It's not specialized, so it's not very good. You can mill with a robot, but it's not very good. It's not fast, it's not very precise. But you can do thousands of other processes, because when you buy the robot, it comes without hand, just the wrist. And the hand is something that is open to definition. Certain definitions exist. You can weld, you can mill, and so on. You can buy those applications. Or you can invent new ones. So the tools, the hands, and the sequence of steps that are adapted to the process you have in mind. So suddenly, the design task is not only to produce data for something, but also to solve the other part, to define how this data will meet the physical world. And this is something, now I use the term duty. It's a duty because if you don't do it, nobody else does it for you, or you're again stuck in a specialized process. But we think this is an enormous freedom that brings us back in the definition of our profession to a pre-industrial era, where things were not that standardized, and designing something also meant to build it. Sometimes, if you go back to pre-Renaissance times, so the master builder was not just designing, but was also building. It was a kind of a holistic act to bring those things together. And this is what this machine pretends from you, or allows you to do conceptually. And then there were another couple of very interesting advantages. The robot is not really a high-tech machine because it's a standard in industry. This means it's a cheap machine because it's a mass product. If you compare it with other tools that are much less sophisticated but cost much more money, just because millions of them are sold, because it's a tool of industrial, the second phase of industrial revolution. And last but not least, it's big. You know, it's not model scale. This machine is able to address a building envelope that is what the last century has defined as the size of prefabrication. So what can be transported without too many complications from a factory to a building site and then lifted. So it's about 7, 8 by 3 by 2 or 3 meters. What you can put on a truck. Now, in the last years, we have been experimenting with this machine in very different setups. We have transported the machine on site, for example. You will see in a project later. We have put the machine on caterpillar tracks, for example. So in order to explore how this concept or this method of prefabrication that is implicit in the first setup, where the machine is bolted, fixed on the ground, could be brought back to the direct intervention on the building site. That is the case here. So where you put the material in its ultimative place without any need to move it again later on, what gives you a completely new or old range of possibilities, of perspectives. I'll talk about this later. Or like here, this is a new lab that we will set up soon at ETH Zurich to have collaborative robotics. So just by allowing 2 machine or 2 robotic arms to interact on the same thing, you can, of course, extend very much the range of possible processes, because suddenly one machine can hold something and the other can do something, and then the other holds it, and the second machine takes a new part, and so on. So this repertoire gets much bigger. So, but this was just technology. Now, with this image, I would like to come back to the, in our mind, central question. If you address machines in materialization of architecture, and in the specific case robotics, but doesn't have to be robotics, it's more the automation. It's what is the relationship between the human, and the human is ourselves, the designer, but the human is also the worker on the construction side doing specialized or unspecialized work, and these new machines. Because we believe that this step will only be successful, at least in the construction domain, that is very different from car manufacturing, for example, because it's so much more complex. Maybe the car that looks more complex than a building, but the construction site and the logistics around it and the parties involved are so much more complex. We believe that this step will only be successful if we do not think in terms of automation anymore. Automation belongs to the 20th century or to the 19th century, to industrial revolution. So how do I automate a job that was formerly done by a human, by rationalizing it, by simplifying it, and by, in the end of the day, substituting the human with a machine. And this also has generated this deep conflict that is still in every discussion we have about machines, that is the conflict between the human and the machine. You know, that is a conflict that starts in the 19th century because it was about labor, and still is to a large extent. But we think that if we look at it at this relationship in different terms, in the post-industrial information era, and recognize that the machine is not here to substitute the human, but just to integrate the human, to give the human a possibility to do things that the human would not be able to do or just not be so good at, then suddenly this conflict dissolves. Because you need both. You need the machine and the human, and you need, and this is then the design question again, you need interfaces that allows the human and the machine to communicate in order to distribute these tasks or the strength the machine has. And we live with this. I mean, we all have mobile phones. There, the tasks are distributed. You know, you would never pretend to be better than your mobile phone at learning phone numbers. You know, so you delegate to this machine, but you don't feel sort of in conflict with your mobile phone because the mobile phone is taking care of remembering 3,000 phone numbers. You know, but when it comes to thinking and to making decisions, then probably even if you have Siri, you better take them yourself. You know, so this same new balance between the human and the machine has to be established also in the physical world of production that until now is still very dominated by this conflictual paradigm. I put the machine and I take out the human, but this doesn't work like this in this new century. This is our assumption. Now, quickly a short diagram to maybe sum up a bit this concept I've been speaking about. So what is design about? Is about the production of data, to the design, what is here defined or called computation. Then we have the material. The material is needed if you want to build something in physical world. And those two components are the classical components of design. So I have a material and I have the definition about where the material has to go. What we bring into this equation, in this triangle, and we say it's not a sequential, the last step in a sequence of actions, but it's a parameter that has to be defined and studied at the very beginning of a project is the fabrication. So how is this material going to be put at the right place according to the design data? And what we here what we think is that only if we look at those three domains from the very beginning on,